Good morning, dear colleagues. So my name is R Viter. I've been recruited by FOTONIKA LV from Ukraine, from Odessa National University. So I've been here since 2012, and I hope I will continue my fruitful collaboration with this, let's say, not consortium, but I don't know, association. Yeah. Last year I got a kind of position of senior researcher here in Fotonika, and here I want to represent the main important results which were obtained together with collaboration, with Latvian scientists and with scientists outside of Latvia. So the topic of the presentation is dedicated to the development of novel photonic materials. So in this case, the photonic materials are like materials which have like advanced optical properties like absorption or photoluminescence or like reflectance. And the main issue of the modern science, optics and nanotechnology, is how to deposit these nanomaterials and how to tailor the properties. So mostly our work was focused on metal oxide nanostructures because of the properties. So these materials can be applied in different applications, in sensors, biosensors, in solar cells and optical coatings, because they have like wide band gap, and so they are optically transparent in visible range. So and they also have good optical properties like room temperature photoluminescence when you decrease the grain size of the particles to nanoscale. Also, these materials have advantages as for industrial applications, as low cost, and there are a lot of methods for deposition, and you can tailor the geometrical parameters of these nanostructures. Like you can deposit nanowires, nanorods, thin films, quantum dots, and electricity. And these particles are stable in aggressive environments, so which enlarges the applications for sensors and biosensors. So for deposition of these materials, we started collaboration with the University of Montpellier. They are chemists and we are physicists, so we put together two expertises and we managed to do metal oxide nanostructures deposited by atomic layer deposition. The advantages of this method is that it can be used also for different purposes. You can grow thin film layers, you can coat different surfaces, and there's no matter which kind of geometry of the substrate you want to coat. So you will have conformal and uniform coating, and you will control thickness, and you will control the chemical composition of the coating what you deposit on the substrate. So here you see the principle of atomic layer deposition. So it works according to chemical reaction. So you deposit the water on top of the substrate, and then using some using some pulses of chemical precursors, you substitute the organic radicals with oxygen and OH groups. So finally, at the end, you will have zinc oxide with you have monolayer of zinc oxide with OH groups on top. So when you repeat the cycle, you can deposit the second layer, and finally you have the continuous growth of this material. So this is the SEM of zinc oxide, grown with different thicknesses. And the most important was investigation of optical properties. So the optical properties were showed that these thin films showed photoluminescence excited by solid state laser with the 325 nanometer excitation wavelength, and it was found that thin films didn't show any photoluminescence because they were mostly amorphous, and surface effects dominated. So luminescence didn't rise because of depletion layer and because of like surface states with non-recombination photoluminescence. So the next step was to tailor the properties to decrease, to tailor the properties of these materials, and we deposited composite materials called nanolaminate. So they consisted of two types of materials: aluminum trioxide and zinc oxide. So firstly, aluminum trioxide was deposited, and then zinc oxide was drawn on top of aluminum trioxide. So these cycles were repeated to reach the constant thickness of the whole construction of 200 nanometers, and we changed the thickness of the single layer. So here you can see the thickness of when the SEM of this nanostructure with 50 nanometer single layer, and here 10 nanometer of single layer. And we deposited three types of samples with 2, 10, and 50 nanometers of single layer, and we got interesting properties that the addition of aluminum trioxide changed the structural properties. So it improved crystallization of zinc oxide, and therefore it influenced optical properties. So even for 2 nanometer single layer, so we observed small X-ray peak which pointed to crystallization, to initiation of crystallization process inside the films. So we calculated the grain size of this nanoparticle of grain size inside these nanolayers, and investigation of optical properties of transmission showed that we had a kind of quantum confinement effect when we started to decrease the film thickness. So it resulted in the growth of the band gap, and so it was like proportional to, it was so we had a dependence that the lower the grain size, the higher the band gap, and it was in a good correlation with the quantum confinement effect theory for these nanostructures. So, and the most interesting things were observed for photoluminescence. So we had enhanced photoluminescence even for 2 nanometer for thin films, and so it was affected by the change of the structure. So it was the way how to tailor the properties of these nanostructures. But for practical application, it's important to develop nanomaterials with high surface to volume aspect ratio, because when we want to have some sufficient effects, we need to increase the active surface, and we need to increase the role of the surface in these nanostructures. In this case, so we combine two technologies: electrospinning technique, so which produces organic nanowires. So in this case, so you mix polymer solution with organic polymer, and you use electric field to create these nanowire structures. And then you put these nanowire structures inside the reactor, and then you coat all of this nanowire with thin layers of zinc oxide and nanolaminates. So here you can see the typical SEM image of the obtained nanostructures. So this is the transmission electron microscopy of this nanostructure, and this is the nanowire core, and this one represents the crystallites which coated crystallites of zinc oxide layer which coated this organic nanowire. We also got interesting results that even when we start 10 nanometers coating of this organic nanowire, we had good crystallization of the system. We observed crystalline phase that is very important also for optical properties. And then we showed the practical applications of this nanocomposites for gas sensing. So we put this structure into the chamber, and we expose there 150 ppm of ethanol, and in this figure you can see the changes of the photoluminescence versus ethanol concentration. Of course, this is the first step, and we will continue our work, and we will try to make calibration against the versus the concentration. And so this next step is application of these nanostructures inside in biosensors and bioapplication. So for this reason, firstly we used nanorods of zinc oxide, so which had 460 nanometers in length and about 60 nanometers in diameter. So the principle was to use these nanorods as photoluminescence transducer for biosensors. So these nanorods were fixed on the surface, and then we deposited their bioselective layer, and then we started to deposit target molecules. So due to interaction between zinc oxide and bioselective layer, we had the changes in photoluminescence. And in order to prevent it, and then we provide testing of salmonella molecules using this biosensor. And we observed permanent decrease of photoluminescence due to interaction between salmonella and our biosensor. So we obtained the calibration curve, and so in future we try to develop and stabilize these biosensors for practical applications. And the recent research, what we are doing together with the Faculty of Pharmacology of University of Latvia, is cancer cell detection. They are experienced in cancer cell production, but we use these nanorods as biomarkers. So they fix cancer cells on the glass substrate, and then we use zinc oxide nanorods and we mix them with specific biomolecules called antibodies, which are very sensitive to cancer cells, where they selectively bind to cancer cells. So only one type of these antibodies binds to one type of cancer cells. When we deposit we deposit zinc oxide and equipped with antibody on top of this glass surface, coated with cancer cells, we wash. Then we wash all this stuff, and due to interaction between antibodies and cancer cells, zinc oxide will partially stay on the surface, and then we measure photoluminescence. So, and you can see that if you use just zinc oxide and wash it and dry it, so you have one signal. When you use non-specific antibodies which are not bound directly to the cancer cells, so you have a little bit increase, because probably non-specific antibodies can attach to the glass. But when you use specific antibodies, you have huge increase of the signal. So using this technique, you can recognize which cancer cells you have deposited on the substrate, and it might be. So we're thinking about the next step to use this technique for biosensor application for cancer cells. So, and in conclusion, I can briefly summarize that LD technique is good for development of new photonic nanostructure, and this metal oxide nanostructure have a lot of prospects for applications in optical sensors and biosensors. So thank you for attention.